Well, good afternoon, everyone, and thank you for being here. Like Rob mentioned, it is a beautiful day, so I do appreciate that you're here today. It's 5 o'clock. I will be done at 5:30, so you can go outside and enjoy your day. My name is Farah Dawood. I'm an assistant professor of chemistry here at Hamilton, and today I'd like to talk to you a little bit about nanotechnology. So you've probably heard about nanotechnology. You've probably seen some nano things out there. So I'd like to introduce you to this field if you are new to it, and if not, well, welcome back. And let's talk a little bit about what nanotechnology is. So in terms of thinking about nano actually refers to a size in terms of what this prefix actually means. So I have a scale bar here talking about what size is, and if you look on the very end here on the right side, there's Alex, and so Alex, or us humans, we're on the meter scale. So if you take a meter and you shrink it down 1,000 times, we have a millimeter. So a millimeter is about the size of a pinhead. You take a millimeter and you shrink it down another 1,000 times, we have a micron, or a micrometer. And a micron is, you can think of your hair. The width of your hair is a few hundred microns. We take a micron and we shrink it down another 1,000 times, and now we get to what's called the nanometer regime. So we take a meter and we shrink it down 1 billion times, and that's a nanometer. So nanomaterials are materials that are in that 1 to 100 nanometer regime, so very, very small. And this is the area of work that I work on in here, and so I wanted to tell you a little bit about what nanotechnology is, and in particular what nanomaterials are. Well, I'm a visual person. I like to see things, so I thought, well, let's look at what these nanoparticles look like. So here is a penny, and to the right of this penny is a holder that has nanoparticles in there. Well, you'll have to believe me, right? They're there, you can't see them. What I'm going to do is I'm going to zoom in on this little holder right here and show you what these particles actually look like when we get down to that very, very small range. So let's zoom right in. And so here's that holder. We'll keep going. And you might notice that these are colored images. So a typical light microscope will produce colored images, as we've shown here. Now, I'm going to zoom into one of these squares here using a different type of microscope, and this is an electron microscopy image. So when we get down to that very small scale, we can't use conventional light microscopes. So we switch to electron microscopy, which actually we have a great electron microscope here at Hamilton, which I'll show you some images from that later on today. So let's keep zooming in here, and now you start to see little gray particles. And here right now are actual nanoparticles. So there was a lot of zooming in to get to these little tiny particles. So these are actually iron oxide nanoparticles, or rust, and they're about 20 nanometers in length. So just to put things into perspective, this is very small. A red blood cell, for example, is 7,800 nanometers. So it's much, much smaller than even a red blood cell. So these materials are really exciting. There's a lot of technological applications. So I'd like to take you back historically just to think about where we've come and where nanotechnology is today. So this is Martin Cooper. He invented the first cell phone, actually, and this was back in 1973. So some of you in the audience might be familiar with these large cell phones from back then. I remember from the 80s, at least when I was a kid, these big cell phones were around. Well, what might be more familiar is something on this order, our very fast and smart cell phones. So we've come a long way in terms of these large cellular phones to these fast, small, and really smart technology. And why and how have we come there? It's actually because of miniaturization. So making things much smaller has resulted in also making them faster and smarter. So now you have the world at your fingertips. So the reason for that is these very small integrated circuits that are actually built into your phone. So an integrated circuit is about half the size of your pinky, of the fingernail on your pinky. So these are very, very small. And here's a closer look at one of these integrated circuits. You might notice that there's a lot of different parts and a lot of different features in there. Well, if we think about how these are actually made, you can think of it as what a stone carver does. It's a very similar idea. And this is one way of getting to nanomaterials by starting big. So we start with something big, just like a stone carver would do with a big rock. And you carve into that rock the features that you want. So just like a carver would do, we take a piece of silicon wafer and we carve little features into that wafer. And that's done using a method called photolithography. And the end result is actually these very, very small features, and these are the transistors. So these are small transistors that are carved into one of these integrated circuits. So this is this is what one of the integrated circuits in your phone look like. These are very small features, and in fact one of these transistors is about 60 nanometers, so they're very, very small, the feature size. And the reason for, and the fact that they're so small, we can pack a whole bunch of them into one of these circuits, and now you have a very fast and powerful cell phone. And if you think about how big one of these circuits are and how big a nanometer is, you end up with billions, not just millions, but billions of really fast working transistors on a very small chip. And this is why, again, as I mentioned, you have a smarter, much faster phone or laptop or tablet nowadays. Now, you might wonder, when I showed you that scale bar in the beginning, well, we started from the meter end, right? And we kind of chipped away at everything to get to this nanometer scale. Why not start down here? Why not start from the smaller size? If we're so close to the size of molecules, can we actually start making nanoparticles from the molecular end? And the answer, of course, is yes. And this method is called the bottom-up approach. So we start top-down with large materials, and we carve out little features, or we can start from the bottom up where we have molecules and we build onto our molecules and atoms, and we build nanoparticles. So here is, you can imagine, one atom. Let's add a second one, and we can keep going until we have a nanoparticle. So a typical nanoparticle usually is made up of a few hundred atoms. So this particle right here is just a few hundred atoms, and that's really where this magic happens. These few hundred atoms really are what a lot of technology is about. And what I'm going to talk to you about now is, once we make these nanoparticles using these bottom-up methods or in solution, what are the different types of new and interesting phenomena that we see? Now, the reason I pointed this out is, well, I'm a chemist, and I like to make things, and I make things using solvents and solutions. So bottom-up approaches actually look like this. So if you're in the lab, you have a flask, and you start with atoms and molecules, and you build these nanoparticles up from the ground up. Okay, so a lot of the nanoparticles that I will show you from now on will actually just look like colored solutions. That's because they're made in solution. Now, these hundreds of atoms that are gathered together actually create some very interesting phenomena. And why is that? Well, let's look at what's really on the surface of these nanoparticles. Now, if you think about a few hundred atoms making up one particle, and you think about what's really on the surface, like the surface atoms, more than half of the total atoms of a nanoparticle are actually on its surface. And that's where the magic happens, and that's really where things change. Properties change. You start to see things that you don't see on what we call the bulk scale. That's like bigger things that are bigger than the nanoscale. So you start to see different colors, different optical properties, new mechanical properties, thermal properties. Really, the possibilities are endless because it's all about what's happening on the surface here. So let's look at this in terms of an example. Well, gold is something most of us have seen, and well, this is a bulk gold bar. So let's really go bulk, materials here. If you think about the atoms on the surface of a bulk gold bar, there aren't that many when you compare that to the atoms, the total number of atoms that make up this big bulky material. Now, if you go and look at a nanoparticle, which more than half the atoms are really on the surface, nano gold doesn't look like the gold that we're used to seeing. This is what nano gold looks like. It's this beautiful wine red color, and these are what some of these particles would look like. So there's a big difference, and these optical properties are again, because of those very, very interesting surface atoms and these surface features. I'd like to talk about gold in particular because one of the, I guess, the most predominant applications of gold nanoparticles is in therapeutics, in cancer therapeutics. Now, a group out of Rice University, Professor Naomi Hollis, is a pioneer in this work, in this field, and her work is really using gold nanoparticles that she can engineer so that she has therapeutic molecules that are attached to the surface of these particles. And then she can also, her group also uses them to actually destroy cancer cells. So why nanoparticles for therapeutics? Well, remember the size. They're really small, right? They're a few hundred nanometers. They're smaller than a red blood cell. So they're a really good candidate that can approach these large cells and attack them. So Professor Hollis's work is really a two-pronged attack at these cancer tumors, where she decorates the outside of the nanoparticles with therapeutic molecules, and then once they are at the cancer cell or the tumor cell, you can these gold nanoparticles, if you just shine light on them or shine infrared light on them, they heat up and they produce a little bit of heat. That heat can also kill the tumor cells. So not only can these nanoparticles be sort of a drug delivery agent, but they can also attack tumor cells. So this work is actually, this particular work right here, so these are these dead cells shown in red. This work is actually in clinical trials right now, and this was for, this particular example is in using pancreatic cancer cells. So a very interesting field, especially considering therapeutics. So that's one avenue where we see nanotechnology. It's an up-and-coming emerging area. Another area that we see nanoparticles and in use is actually in semiconductors. Now, you may not believe me, but you should. Each of these little bottles contain the same kind of material. So each bottle contains cadmium selenide nanoparticles. And the only difference is that the ones on the left here are 2 nanometers in diameter, and then the ones on the right here are 6 nanometers in diameter. So you might think, really, 2 to 6, that's not a big difference. But guess what? When you take these and you line them up this way, so the size is increasing, and you hit it with UV light, they glow in different colors. So just by changing the size ever so slightly, we can tune the colors that these semiconducting nanoparticles emit. So these semiconductor nanoparticles are actually known as quantum dots. And maybe that term sounds a little more familiar. And I'd like to show you this next slide. And this is Samsung and Sony actually use quantum dot technology now in their displays. So does Amazon in their newest Kindle. So I want to draw your attention to the central part of this screen. So this is a television screen without quantum dots. And then once you add the quantum dots in, there's a more lifelike picture, a more lifelike appearance. So bluers become bluer, reds are redder, greens are greener. You can get those really fine colors that's more like nature, thanks to tuning those little nanoparticles. So I think this is a really interesting and fun area of research, especially considering that now quantum dot TVs, you can buy them there. I was at Best Buy the other day, and I was very excited to see a whole display of quantum dot TVs. It made me very happy. So now coming back to the research that we do here at Hamilton, we don't work with quantum dots, at least not yet, but my research group, we work on 2 particular applications. And one of them is we take nanostructured materials, and we're interested in using them as sensors. So can we take these nanoparticles or nanostructured high surface area substrates and use them for detecting really small levels of toxins. What about biochemical threats? So that's one area of research. The other one is we're also interested in making nanostructured electrodes. These highly nanostructured materials that have a lot of surface area are ideal candidates for using sunlight to produce energy, pretty much, from sunlight, carbon dioxide, and water. So these are two main areas of research that we carry out in my lab. And one real interesting application and one area that we care about more than just nanostructuring is not only do we want to make nanostructured materials, but can we also make them uniform? Now, we want nanostructured materials, but we also want a uniform substrate. If you have a sensor that's, say, that big, and one area of the sensor is better at sensing something versus the other, well, that's not a good product, right? So we want nanostructured surface area, but we want the same thing everywhere. So how do we get to that? Well, our approach is using a template. So these right here that you see on this slide are little polystyrene beads that once they're in solution, they can actually assemble on their own. So we're not applying any electric field or anything. These beads just simply assemble on their own. And that's because this is their lowest energy conformation. They want to be this way. So we use this to our advantage because, well, if our template material wants to assemble, now we automatically have a nice ordered array. And if we look at these assembled nanospheres, so these were actually images taken from using our electron microscope here at Hamilton. This is what they look like, a beautiful ordered array of nanospheres. Now, we want to grow nanostructures within these nanospheres. So what we do is we assemble these spheres, and then in each of these tiny little voids, which are also nice and ordered automatically, nature does that for us, we deposit different types of nanomaterials and we grow them from there. And the idea is that from there we can get more uniform growth so that if we're building sensors and electrodes, we have a very uniform sensing capability. So what do these nanostructures look like? This is just a quick snapshot of some of these really fern-like nanostructures. So these sensing materials that we use are made of silver. They're beautiful to look at. They look like this. They look like ferns. And each of these little ferns on the edge have very, very fine features. These are very intricate, very small materials. Here's another look at one of these dendritic, these are called silver dendrites because they have that shape. And here's another look at what these look like. Again, at the very ends, these materials are very small. They're on that nanometer scale. So we ran a few tests in the last few months to see what do these materials actually do. And what happens is when you have, imagine you have, how does this work as a sensor? Imagine you have a glass slide and you have a molecule of interest and you want to see, okay, can our sensing method detect this molecule? So we started with just a plain glass slide, a microscope slide if you wish, and we deposited some molecules on there and said, okay, with using a certain type of spectroscopy, what do we see? Well, it turned out that on just a flat plain glass slide, we don't really see anything. We don't see any signal, just a flat line. Okay, well, that's fine. So then we thought, well, what happens if we actually build some nanostructures on top and then deposit our molecules of interest? Well, now we start to see the signature peaks of our molecule of interest. So without any nanostructures, we don't see anything. But with nanostructures, we actually start to see things. So nanomaterials in our applications here are more like our eyes. They open our eyes to things that we don't see, things we can't see. For example, like I've shown here, without the nanostructures, we don't really see these signature features of the molecule that we're interested in. So our goal here is to see how small can we go in terms of making the nanostructures, and then also what are the lowest concentrations we can look at in terms of finding, can we use our nanostructures as our eyes to actually see what's going on in there. So to close, I'd like to thank, obviously, this is my research group. I have a great group of motivated really great students. Preeti, Willa, Ida, Aaron, Dan, and Alec, all very good. We work together. There's 3 of them work on the sensor project and 3 of them work on the electrodes. And then, of course, Zoe from the summer, who's here today too. And then I'd like to thank the Hamilton Chemistry Department and the microscopy facility for helping us move this project forward. And then, of course, funding-wise, the Hamilton College, the Edward and Virginia Taylor Fund, and the Clara Booth Luce Fund. And again, thank you so much for being here today. It's a beautiful day out. I am finishing on time, so thanks again. And I'll and I will take any questions.
What are other applications for nanoparticles?
There's, well, I focused on a few here. There's, when you think about miniaturizing things and flow, for example. So there's a whole area of, can we miniaturize little devices, and can we move things from one to the other? So by making very small channels in terms of moving liquids across. So again, building small platforms. So thinking of like a whole lab on a small chip. That's a big area too, and it's all about flow. And again, when these the tubes, for example, that move the liquids across get smaller and smaller, you start to see different behavior. So we can use that to our advantage as well to pretty much change how things flow, how things move, and how these little machines work. Yes?
What's the physical effect that creates the light changing? Is that just the size of particles affecting light waves in different ways?
Oh, with the quantum dots? That's a great question. I teach physical chemistry, and this is what we do. So it's actually, so there's a lot of students here. I'm sure you've heard this before. It's actually, it's a quantum effect where just based on where these electrons can move, by limiting the size of the particle, the electrons are limited to where they can move. So as a result, the size changes with the energy. So when you decrease the size of a nanoparticle, you can increase the energy, the band gap of these semiconducting nanoparticles. It's more in terms of how much energy. So these semiconducting nanoparticles, semiconducting materials have what's called an energy gap. So if you can match that gap in terms of the light that comes in, you can. That's where you see this phenomenon, where you have an electron that's excited, and it relaxes down, and then emits a color. They're emitting light. No, this is not an absorber. Right? This is they absorb a certain amount of light, and it's the emission that changes. Right. And that's a direct correlation to physical chemistry, and it's actually called the particle in a box effect. So I see a lot of students here who are in my class, and so this is something we study. It's my pleasure. I feel bad for them, actually. Yes?
This is probably a very bad question. My brother's a chemist, I'm not. This is the econ lecture. So my question is more around nanotechnology and commercialization. And again, that's why this may be an unfair question. Companies out there that are using this technology that is promising.
So Sony and Samsung are actually right at they're like the real frontiers that have used these materials, especially if you think about these quantum dots, they're using them in their displays. There's so IBM and Intel, they're the chip makers, so they do that top-down carving method of using nanomaterials. And there's a few more. There's a lot of startup companies that actually provide the nanoparticles for a lot of these companies that use them in their displays and such. So there's a lot of growth, but the big companies right now that are actually using them, I would say, are Sony, Samsung, IBM, and Intel.
Is GE in that mix also?
And GE, of course, right here in Utica, there's that's right. GE and AMS is also they're building facilities for pretty much bringing in chip work. Yes.
Is there any interplay between nanoparticles and subatomic particles and all the stuff we see in science newspapers?
That's going into a whole nother realm of right. There's not necessarily, because here we're really talking about surface effects, and so when you go to subatomic, it's a whole nother world in terms of you're not really thinking about atoms now. With nanoparticles, it's really thinking about atoms and how these things work on the surface. So I think we're just out of time. Thank you once again for being here and for all of the talks.